Now that we prevented dictionary attacks by using salts, the attacker can now perform another attack, that is the exhaustive search or brute force attacks, which is actually trying every possible password. So when a hash and a salt value is obtained, these can be obtained when a database leaks. The attacker calculates hash of every possible short passwords and check if the hashes are identical. So this way, the attacker can capture the password. So if the chosen password is short, then the attacker has to try less possibilities, and this way it will be easier for the attacker to capture the password. So this is why it is always recommended to use long passwords. But how long it should be, it is not that well defined. So in the literature, if you just Google it, or for instance, people say that using 8-character passwords are good enough. But actually, this is not the case, because all of those calculations were done by considering the computational power of CPUs. CPUs are a lot faster and has more cores now, but GPUs or FPGAs can also be used for password cracking. So believing that an 8-character password is secure is not a good idea. So let's see why this is the case. So assume that we are using the English alphabet, which is most of the case the situation, because for instance in Turkey we try to avoid using Turkish characters in our passwords, because sometimes it fails because they store it wrong in the database, and the next time you try to log in with your Turkish character password, the authorization fails. So most of the time people choose English alphabet letters. So English alphabet has 26 letters, and if you use also capital letters and the small ones, this gives you 52 characters. And if you also use numbers, then you get 62 possibilities. But on your keyboard, generally there are 94 printable characters if you're using the ASCII table. So in other words, English alphabet and all of the possible special characters that you can print on the screen with your keyboard, there are 94 possibles. So assume that you are choosing an 8-character password, and assume that you are only using the small letters. So this way you can actually choose 26 to the 8 different passwords. This number is this, but I'm going to write it in terms of powers of 2, because this way it is easier to see how secure they are. Because for instance, with a GPU, performing 2 to the 30 or more hashes in a second is possible. So this can actually be broken with 2 to the 7 seconds, or if you have 2 to the 7 different GPUs, it will take you 1 second to break the system. So these passwords are really not secure. But when you are creating a password, the web pages always recommend you to use also a capital letter and use a special character, or they are not allowing you to create your password. So let's see what happens. If you also use capital letters, now your password space really increases 2 to the 45. If you also use numbers, now you reach 2 to the 47, which is not that much of an increase because you're adding extra 10 characters. But if you consider all of the printable characters on your keyboard, this gives you a space of 2 to the 52. But this number is not large. Even we can break this, which has 56-bit keys, and you need to perform 2 to the 56 operations to perform a brute force attack to capture key of a DES algorithm. So 8-character passwords takes less time to be broken than DES. And we stopped using this in the 1990s. So imagine how easy to break this. For a GPU, I think for a single GPU, this means it will take a few months. But if you have more GPUs, then you can do it in days or actually in a few minutes. So this way, it shows that 8-character passwords are not secure. So we can search the space in a clever way also. For example, users select easy to remember short passwords. They almost never use more than 2 special characters and so on. So actually users are using capital letters, numbers, and special characters because the web page asks them to use it, so they only use once. So you don't have to search this whole space. If you search the in a clever way, a very small subset of the search space would give you almost every password that has 8-character length. So what can we do? We can ask users to choose longer passwords and use a lot of special characters, numbers, and so on, but this will be very hard for users to remember. You can always use some applications to remember your password, but again, you have to check the security of those applications, because at that point you are giving your security to the third-party application. So we cannot ask users to choose very long passwords. So countermeasure is to slow down the hash computation speed. So this way we can be more secure against exhaustive search attacks. So idea is as follows. Instead of using the hash value of a password and the sol concatenated to it, calculate this hash value, but instead of storing it in your database, take this as an input and perform another hash operation. And repeat this process thousands of times, and at the end obtain a hash value and say that this is the hash of the thing that you are going to store in the database. For instance, if you choose 8192, I chose this number because it is the power of 2. So if you perform this hash operation this many times, then what you get is as follows. When the attacker captures the hash, they have to perform this many hash operations to try a single password. So if you go back to this picture, all of these numbers has to be now multiplied with this. So for instance, if you choose this operation to be performed 2 to the 10 times, this cost would increase by 2 to the 10, which will be, for instance, if you increase this number to 2 to the 62, it will be a lot harder for that hacker to perform this many trials. But of course, you can choose this number even larger. So let's see an example in the literature, and we can see what kind of choices people are choosing. For instance, for this scenario, Winrar chooses 2 to the 15. So this actually adds 2 to the 15 to all of these numbers. For instance, 8-character password becomes, to break them, you have to try 2 to the 67, which would be very hard for the attacker to perform. Okay. So we will talk a little bit about this at the end of the slides, but now let's move on to another usage. So we always said that cryptography keys has to be chosen randomly, and we cannot ask a users to randomly choose an AES key, which is like 128 bits. So we cannot a user to choose 128 bits from their mind and write it as a secret key. So most of the time we use random number generators and so on, but this way we don't know what the secret key is. So that most of the time the software is performing this operation in the background and chooses a key for ourselves. But you have to be in control of your keys. So one way is to generate keys from passwords. So this is why these algorithms are called password-based key derivation. And password-based key derivation function 2 is one of the famous one. It is a function that is part of RSA Laboratories public key cryptography standards. This is also published in RFC 2898, and a lot of applications are also using it. For instance, you can use it for full disk encryption and so on. So idea is as follows. Instead of choosing a secret key, choose a password and choose a hash function, use it in a message authentication code way, and use a salt, and indicate how many times this hash operation will going to be performed. And here you represent the desired key length. So here is actually the explanations. So pseudo-random function just takes two parameters. We will see in an example how it takes these values and how it can be defined. C is the number of iterations desired. Dk len is the desired length of the derived key, and at the end you obtain dk, which is the generated derived key. So let's look at how this algorithm works. Each hlen bit block ti of the derived key dk is computed as follows. So you need to generate ti's and concatenate them to obtain the desired key. So generally we need short keys. For instance, for block cipher encryption, we need 128-bit or 256-bit keys. But for public key algorithms, we might even need a key length that is larger than 10,000 bits. So this is why this algorithm actually supports almost any length desired key. So these TIs are calculated as follows. You have the f function, which takes input password, salt, c, and I. So where f is the XOR of c iterations of the chained pseudo-random function, and it is designed like this. So this is the idea. For ti, you need to perform this operation, and all of these UIs are actually the password, salt, concatenated to the actually the big endian representation of the 32-bit value I. So it is like this. Okay, so let's see a concrete example. VPA2 uses the password-based key derivation function 2, and it uses like this. For the pseudo-random function, it chooses SHA-1, but use it in the HMAC mode, which is a message authentication code. So it is not only a hash function, but it's a message authentication code. So it takes two inputs, the message and the key. And your passphrase, remember that when you use Wi-Fi, you choose your SSID and password. So these are going to be used for the SHA-1 input. So as the message and the key for this HMAC, you take these two values. So how many times you are going to perform this HMAC operation is defined as 4096, which is actually 2 to the 12, right? So which is not that the large number actually. And your desired key length is 256 because you are going to use AES 256. So this is a concrete example where you use this password-based key derivation function. So if the passphrase is short or easy to guess, then you can attack the system. SSID is not secret. If you're close to the router, you obtain it. So as a salt, they use SSID. So if you go back to picture here, you can see how they are computed. So initial U1 is HMAC SHA-1, your password, your SSID concatenated with the public knowledge, and that is your U1. And then you take this U1 as the next salt and use your password, put them again for SHA-1 HMAC, and continue this way until you get the desired length of password, sorry, key. So another example is Winrar. So Winrar's password-based key derivation function uses HMAC but SHA-256. But of course, older versions of Winrar was using SHA-1, but a few years ago, they moved on to SHA-2, which is more secure. And they use it this many times. I think for the key derivation, they use it 2 to the 15 times. But when you choose your, when you try to decrypt and decompress the file, you have to type in your password. And instead of decrypting, they first check if this password is correct. So in order to do it, you perform 32 more hash operations, and the output is actually stored inside the file, and the Winrar checks it, and if they match, then the software allows you to decompress and decrypt. So it is pretty secure. As you can see, the number is huge, but how secure is, I will show you in the next slide. And our analysis shows that Winrar passwords longer than 8 characters are secure. So let's see why this is the case. So a few years ago, we performed an experiment. Since SHA-2 is used in cryptocurrency mining, a lot of good optimizations are available for the GPU. So we choose a GPU, which was a good one at the time, but today we have a lot better, and checked how long it takes if you choose your password only consisting of numbers. If the length is 13 characters, then it will take 20 years to break this password. So using only numbers is not a good idea, as you can imagine. But let's see what happens when we don't use a special character. So assume that you chose your password to be of length 6 characters, and you use numbers, small letters, and big letters, so capital letters. So you didn't use any special character. On a single GPU, it will take 41 days. And if you increase your password length, it increases exponentially. Now it will take 7 years. If you choose 8-character passwords, I'm talking about Winrar here, so it will take more than 400 years to break your password. So you shouldn't also see it as a hacking operation. For instance, in a file in your computer, you chose your password years ago. You know that it is short than 8 characters. You know that you didn't use any special characters, but you forgot your password. So with GPUs, you can perform these operations and recover your password. So let's also see what happens if you choose all of the printable characters. For a 6-character password, it will take more than a year. For 7 characters, it takes more than 100 years. And if you choose 8-character passwords, it will take 13,000 years on this GPU. So you might see that, okay, these lengths are secure, but actually you have to look the picture in this way. This is an old GPU. It has it has 1,664 cores, I guess. But now we have GTX 3000 GPUs, which are around 4 times faster than this one. So you can divide all of these numbers by 4. And you will say that, okay, these numbers are still huge. Sorry. But the idea is that even for this number, you might say that, okay, 13,000 years is a long time. But 13,000 people on the internet get together as a distributed system, and instead of playing games, they can capture your password in a year by performing the exhaustive search attack. So as I told you, since this current GPUs are a lot faster, breaking 8-character passwords in a few days is possible if you have around hundreds or thousands of gigabytes. So this is why we recommend people to use at least 9-character passwords. Otherwise, you wouldn't be secure. So let's finish it with the password hashing competition. As you can see, password hashing is everywhere, even in the cryptocurrency mining and so on. You are using hash functions, but there wasn't the established standard to fulfill the needs of modern applications and to best protect against attackers. So there wasn't much standards at the time. So this is why this competition, PHG, password hashing competition, was initialized by Jean-Philippe Amoson in fall 2012. The website is still available. You can go and see how this competition was performed, what are the candidates, and who win and what is the specifications. But to give a short info about the competition, it had received 24 submissions. 9 finalists were announced in December 2014. And in July 2015, Argon 2 announced as the winner. So it is a good algorithm which you can check the web page and see how it works. But other 4 finalists are also received special recognition. These are Catena, Lyra 2, Magwa, and YesScript. This special recognition was things like side channel resistance and so on. So you can learn more about them in the web page. You might heard the name Lyra 2 before, because some cryptocurrencies use this algorithm to protect their mining operation against FPGAs. So they want their algorithm to be mined by GPUs, but they tried it to be hard to build ASICs so that GPUs can continue to mine these cryptocurrencies. But of course, this kind of ideas most of the time fail. They update the algorithm, so you will see revisions in the internet and so on. But there wasn't a good standard, and this competition actually was to choose an algorithm so that it will be standardized everywhere. But as far as I know, not much people know this competition, and not many people heard the Argon 2. So it is my job here to actually talk about this, so that now more people know about this competition, and they know they have more hashing algorithms for their security of passwords.